Let's consider, as an example, a circular wedge. This just means a wedge of a circle. Imagine a piece of pie that's cut into quarters. So we have this wedge. Let's say the radius of that wedge is 3. So we have 3 here, 3 here. Now that wedge can be described in a number of ways. We can describe that in we can describe the wedge in rectangular coordinates as let's say 0 less than or equal to x less than or equal to 3, and 0 less than or equal to y less than or equal to the square root of 9 minus x squared. I'll leave it to you to work out the details of that, but it comes out very simply because this circle is defined among other things by the relationship x squared plus y squared equals r squared, x squared plus y squared equals 9, and the solution comes out very easily. We could also describe it in terms of y cross sections, 0 less than or equal to y less than or equal to 3, 0 less than or equal to x less than or equal to the square root of 9 minus y squared. We have a nice symmetry in the circle that isn't there in a lot of other types of shapes. Now, that would lead us to integrals, like a typical integral might be 0 to 3 and 0 to the square root of 9 minus x squared of some function dy dx. And we've already seen that. Depending on what the function is, this wouldn't necessarily be a particularly bad integral. Another way of describing this wedge is in polar coordinates, and in polar coordinates it's even simpler than it is in rectangular coordinates. In polar coordinates we see that our angle theta goes from 0 to pi over 2. So we could say 0 less than or equal to theta less than or equal to pi over 2, and r goes all the way from 0 out to 3. So we have 0 less than or equal to r less than or equal to 3. So if we set up an integral in polar coordinates, we're going to have a double integral, but none of our integral limits will be functions of any of the other variables. So there could be one considerable advantage to using polar coordinates for a region that fits the polar description easily, as does this one. There can be other advantages to polar coordinates, and we'll set up this integral in a minute. We'll set up an integral in polar coordinates. Let's assume a function like this, and this might be considered to be a density function. How about 1 over the square root of 1 plus x squared plus y squared? Well, we can put this function as it's written into either of these, well, into this form or into the integral for the y form, which would be very similar because of all the symmetry in these expressions. So that would be okay, but then we'd have to find an antiderivative of 1 plus x squared plus y squared with respect to y if we set it up in this order, with respect to x if we use this. Now that's actually not particularly difficult to do, but it's more trouble than we need to go to. This ends up much simpler in polar coordinates because, let me just reiterate something I assume you know, that the connection between polar and rectangular coordinates is that r equals the square root of x squared plus y squared. Theta for a given point xy is the arctangent of y over x plus 180 degrees or pi radians if x happens to be negative. And similarly, we can go from polar to rectangular coordinates. X equals r cosine theta y equals r sine theta. What we have here is an expression in rectangular coordinates that can be written very easily in polar coordinates. Now the function as I've written it here is simpler in polar than in rectangular coordinates, but I really intended a slightly different denominator here, so I'm going to make a change. What I really intended was that this denominator be 1 plus the square root of x squared plus y squared, which means that the denominator is going to end up being 1 over 1 plus r. Let me make that modification before we go on. I've made the modification in our function f of x, y, so that using these conversions or these facts, we see that f of r theta is just 1 over 1 plus r, square root of x squared plus y squared being r. That function is going to be a lot easier to integrate than 1 over 1 plus the square root of x squared plus y squared. Now we'll start analyzing this integral, having made these changes, understanding what our polar region is, the definition of our polar region. And what we need to do is we first need to partition our intervals and see what that means. And we're going to continue that in the next clip.